Hello, friends. Welcome to the Nexus podcast. I'm your host, James Dice. Each week, I fire questions at the leaders of the smart buildings industry to try to figure out where we're headed and how we can get there faster without all the marketing fluff. I'm pushing my learning to the limit, and I'm so glad to have you here following along. Before we get started, here's a quick note from our sponsor. A quick note from our sponsor, enVerid Systems. We've discussed this a few times on this show in the past. Improving indoor air quality with optimized ventilation and air cleaning doesn't need to conflict with building decarbonization and climate resiliency goals. To show you why that's true, enVerid Systems and a group of other IAQ and energy experts put together a new white paper called How to Achieve Sustainable Indoor Air Quality. Check the link in the show notes to learn how a 4-step clean first approach can be used to design and operate low energy but high IAQ climate resilient buildings of the future. This episode is a conversation with Christian Weeks, CEO of enVerid Systems. Christian and his team just published a new white paper on sustainable indoor air quality, and it's really great. And I'm serious about that. I learned a lot from it, and I love how much knowledge from the pandemic is condensed into it. And I think the way they took a stand and made actual recommendations amid all the IAQ confusion is going to be really helpful to the industry. So we unpacked this white paper and the main 4-step framework at the heart of it. A quick community announcement too. Now that cohort 5 of our foundations course is launched, I wanted to make sure everyone knows that we also do private cohorts. So all of you do onboarding when you hire new people. Think of this as industry onboarding for your team. We host teams of 10 or more and teach the smart buildings industry to them in a private setting, all discussing your context and how you exist in the industry. So hit us up to get on our schedule. And without further ado, please enjoy the Nexus podcast with Christian Weeks. Hey, Christian, welcome to the show. Can you introduce yourself?
Thanks, James. It's great to be here. My name is Christian Weeks, and I'm the CEO of enVerid Systems.
All right. I love to start with people's backgrounds. So that is the present day. Take me back. How'd you get here?
Well, I have been with enVerid for a little over 3 years now. But before enVerid, I spent almost a decade with Enernoc. So I've been in the sort of clean energy building efficiency space for some time now. I had a fun run at Enernoc, which is, for those who aren't familiar, a Boston-based energy efficiency and leader in demand response in particular. Focused on commercial industrial customers. So I had various sales and marketing roles, marketing sort of roles, and ultimately ran a number of different business units within Enernoc. I had a fun stint for your listeners on down under in Australia and New Zealand for a couple of years, and then came back and ran our global demand response business. And then we were acquired by Enel, the Enel X part of Enel, which is really doing a lot of innovation in the energy services, energy efficiency space. And so worked with them for a year running the North America business, and ultimately got the itch to try something new and get in a little earlier. So I found enVerid, which is we'll talk more about enVerid, but an earlier stage business also based in the Boston area. So that was really my sort of the bulk of my career in the energy space. Prior to that, I did an MBA, and before that was in management consulting.
Got it. And Enernoc, there's quite a few Enernoc alumni that are out in different places, right?
Yeah.
So there's like the Hatch Data folks, and that's the most prominent example, but you probably have a bunch of others as well.
It's, I had a business school professor who, when asked, would provide some career advice, and he said, as much as the company you choose and the role, think about the tribe you're joining. And I had a lot of fun at Enernoc, but one of the fun things that continues to sort of give there is that when I go to like a clean energy networking event in Boston, like I did a week or two ago, it ends up being like a mini Enernoc reunion. Undoubtedly, I'm going to run into 2 or 3 people that were there with me, and it's always a lot of fun. So yeah, it was a great group. It's a vast network. I think it's one of the things that Tim and David, who founded Enernoc, are most proud of, is not just what we did at Enernoc, but the legacy that created and all the different ventures that have spun out from Enernoc and the people who grew up there and are off doing other interesting things in the energy space. So it was a privilege to work there, and it's been a lot of fun to keep those connections going and bump into people here and there.
Yeah, that's cool. So enVerid, can you tell me about the founding story of this company?
Sure. So enVerid was founded in 2010 around a kitchen sink in Newton, Massachusetts, not far
Okay.
from where our headquarters is today. It's founded though by two Israeli Americans who were technology backgrounds. They were both PhDs. They were also entrepreneurs. Both had run companies before, earlier stage companies before, and they were looking at sort of thinking creatively about their next venture. And they hadn't done anything in the building space, but had some ideas initially related to indoor air quality. In fact, the initial concept they were toying with was around increasing oxygen levels in buildings to try to improve productivity. But what they discovered in investigating that a little bit was that the air in buildings, the volume of air in buildings is replaced like 20 times a day in a typical office building. So it's constantly being replaced. So pumping in more oxygen was just going to kind of be not so productive because you were going to displace it, replace it so many times. But what that led to was the idea for enVerid, or the insight that spawned enVerid, which is that we are replacing all the air in buildings 20 times a day. And the question was, well, why do we do that? Well, turns out we need a little bit of that to balance the building, offset the toilet exhaust and kitchen exhaust and all this. But most of that outside air, 80% of it or so, is actually to clean the indoor air, to dilute indoor generated contaminants so we can live and work in healthy environments. So that was sort of what got them really thinking, well, gosh, that's so energy intensive. There must be another way to maintain good indoor air quality. And it, led to, well, why can't we clean the indoor air? And then it led to, well, spaceships and submarines can't bring in all this outside air. So what are they doing? Well, yeah, they're cleaning the indoor air. So why can't we do that in commercial buildings? So that was really where that's sort of the founding story. And we'll get more into the solution that we developed and how we're going to market, I'm sure. But that was the inspiration. It was outsiders to the industry, poking around a little bit, first focused on health, then realizing this huge inefficiency and starting to think about, well, how could we address that? And here we are a number of years later, working away at that, solving that problem.
Mm-hmm. Yeah. So you come from Enternock and you saw this startup and you're like, I can help them.
Yeah.
What was the decision to join?
Right. They were looking for some help, with just the scale up commercialization activities. And that's really what I, consider one of my strengths, something I really enjoyed sort of participating in at Enternock. And I was looking for, a earlier stage, but growth stage business in the clean energy sector in Boston. I'm sort of from here and wanted to stay in the area, and was poking around. And when I learned about enVerid and and started digging into what Udi and Israel originally dug into, like, why do we ventilate buildings and how much does that contribute to the building energy load? And geez, it really isn't efficient. How do we do it? And then the technology. I mean, at a conceptual level, it was so elegant because it was so simple. It's like, let's just clean the air in the buildings rather than replace all this air 20 times a day. Yeah, that makes a lot of sense. Can we actually do that? And then digging into technology, and they had good traction, some really good initial customer stories, case studies. And so I said, well, this sounds like a really big opportunity and a really interesting technology that had a lot of IP around it and was, well vetted. And it was like, yeah, I think I could help grow a business like this. And so, that was intriguing. Right. and led to my coming on board in the beginning of 2019.
Totally. All right. So what are the different products that you guys, and how do you go to market with them?
Yeah. So the underlying technology that enVerid has developed, where the products are based around, is a sorbent media technology. So it's probably good maybe to start just talking about what that means.
Yeah.
So a sorbent, sometimes they're called adsorbents, basically a material that is designed to capture a particular gas or maybe a mix of gases from the air. What happens is as air passes over a sorbent or adsorbent or through a sorbent filter, which is what we do, essentially the gas molecules in the airstream chemically stick or bond to the sorbent media and are held by the media. So what we essentially do, sort of the core innovation, is a specific sorbent media blend that we developed to address a wide range of gaseous contaminants that ASHRAE has identified as contaminants of concern. In other words, contaminants that need to be controlled if you're going to displace outside air ventilation with clean indoor air. So from the beginning, we were designing around those contaminants and essentially trying to take that concept from spaceships and submarines, which was proven and validated, but make it commercially viable and primarily economical for commercial buildings. So what we came up with was a unique sorbent media that is unique in the sense that addresses a wide range of gases and does it very efficiently and cost effectively. And we came up with a way to deploy that in commercial buildings by essentially creating these sorbent filters. So think of your particle filter, like your MER filter, but instead of just being sort of having filter paper, we actually load these filters up with our sorbent media.
Okay.
So it's like a 2x2 is actually weighs like 15 pounds because it's full of this sorbent media.
Wow. Okay.
And what we do is we install those filters. Today, we're actually putting these systems with these filters directly in air handler units and rooftop units through a partnership we have with Daikin Applied. But before we got going with Daikin, and still today, we're also deploying these filters in buildings as part of a air cleaning module that we've developed. So a separate mechanical system that is modular in form. Each one cleans the air for about 20,000 square feet. Okay. And we essentially integrate these air cleaning modules with air handlers or rooftop units to clean the air in the space and allow that cleaned air to then be recirculated back into the area and at the same time reduce that outside air requirement. So we're delivering clean air, which is the goal, but doing it with a higher ratio of air cleaning to outside air ventilation, which is where we get the energy efficiency benefit. So the products are these what we call HVAC load reduction or HLR modules. These are these systems that do exactly what the name indicates. We're fundamentally reducing load on the building, heating and cooling loads on the building by cleaning indoor air. And these modular units serve, again, about 20,000 square feet each. We have different form factors to go outdoors, so they're more weatherized on a rooftop or inside a mechanical room, or even on a floor with a 4x4 configuration or in a space directly. So different form factors for different types of applications. But they're basically a system that's bringing about 1,000 CFM through the unit, running that airflow over through our sorbent filters. So we're capturing all those gaseous contaminants or listed, ASHRAE contaminants of concern, and recirculating that clean air back into the space.
Got it. Yeah. Got it. Very cool. So once this gas is collected, talk about the maintenance side of this. Like, do you have to recharge the sorbent with new chemicals? And then where does this gas go that collects after that sticks to the material?
So our sorbent filters capture a wide range of gases in compliance with the ASHRAE standards, and we essentially hold those gases and just need to replace the filter every 2 years.
2 years.
So maintenance on the system is replace the filter once every 2 years, and you're good to go. Now, we do have a premium product that not only addresses the gases that ASHRAE has identified, but also removes CO2 from indoor air. Okay. CO2, interestingly, we'll probably get into this a little bit later, is not considered in and of itself a contaminant of concern at the levels that are typically found in buildings. But it's often used by people as a proxy or indicator of occupancy or of overall ventilation effectiveness. So we may get into that a little bit later, but CO2 is not necessary, does not need to be controlled under the ASHRAE standard to do what we do. But many people have been paying attention to CO2 and are concerned about CO2. And so we have a version of our unit that also removes CO2. But when we do that, because CO2 is in buildings at parts per million levels, much higher levels than gases, which are parts per billion, our filters do fill up, saturate with CO2 molecules. And when that happens, we do have in this higher end product a regeneration process where we can use heat to re-excite those molecules that we're holding on to and release them. And what we do is we vent them outside the building. And that way we essentially recharge the filter so it can be used for 2 years, just like when you're not also removing CO2, but we just need to add that heating element, that regeneration process, so that they are useful for that long.
Interesting.
So it's essentially a more efficient way to capture CO2 and vent it outside the building than traditional dilution ventilation. But it's not considered a contaminant of concern at the levels we find in most buildings. So it's not part of the ASHRAE building code and is really an option, an additional feature if people want it, but isn't critical.
Cool. What about, so the typical ventilation design process, right? So you mentioned ASHRAE, you mentioned dilution design.
Yeah.
Traditional ventilation design process is like this formula and this process that designers go through. I did it when I was early HVAC designer
Yeah.
many years ago. But how is that process modified when you have this
Yeah.
device in the building? How does
Yeah.
that work?
So we work very closely with mechanical engineers, and we have our own team of mechanical engineers to provide design assist services.
Okay.
Essentially, what we do, this whole concept of cleaning indoor air and displacing that outside air ventilation requirement with clean indoor air is allowed for under something called the Indoor Air Quality Procedure, or IAQP, which is a procedure that's described in ASHRAE standard 62.1, which is the ventilation standard for commercial buildings.
Mm-hmm.
There are in ASHRAE standard 62.1, there are two procedures to determine mechanical ventilation rates. One of them, and the one that's most familiar to people, is called the ventilation rate procedure.
Yeah.
And when you apply the ventilation rate procedure, essentially you use a table and determine minimum outside air based on occupancy, sort of how many people you're designing the space for,
Mm-hmm.
and also based on area. And it has both components because you've got indoor generated contaminants that are associated with people. So that's the occupancy component. And you have indoor generated contaminants associated with the space, the paints, the glues, and the furnitures, and these sort of things. And so you get the area component. So those two together give you your ventilation rate if you're using the ventilation rate procedure. The indoor air quality procedure, which is sort of right next to that in the standard, has been in the standard since the early 1980s, is similar, except it's performance-based rather than being prescriptive. And by performance-based, I mean that it allows you to determine how much outside air you need,
Mm-hmm.
accounting for specific contaminants and design targets, which ASHRAE has now defined, and also it allows you to account for the cleaning efficiency of something like our system.
Okay.
So in other words, it allows you to say, in a typical building, I've got these contaminants that are going to be generated at this rate, and I can remove them at this rate with this air cleaning system. So I can use the air cleaning system to address a good portion of that IAQ requirement, and then I'm going to supplement that with outside air ventilation to deal with building pressurization. If I need to top up what I'm doing with air cleaning, I can add that ventilation,
Totally.
as well. So it's basically, it's performance-based and allows you, the nice thing about it is it's a more direct way to design to specific design targets. So, the ventilation rate procedure is based on sort of rules of thumb about, what the resulting design will generate in terms of different measures of indoor air quality. With the IAQ procedure, you can actually use specific targets. You can use the ASHRAE minimums, or you can use the LEED targets or the well building, targets, and design to that. So a little more directly or explicitly what you're designing to, and then you get the benefit of incorporating the air cleaning to get that more efficient design, because you're not just relying on outside air ventilation, which in many climate zones is very energy intensive and expensive to design for. So that's essentially what we do with engineers is if they're not familiar, or maybe many times they're familiar with the IAQ procedure but haven't actually applied it, and aren't familiar with the tables where ASHRAE lays out the contaminants and the design limits, or aren't familiar with the calculations you need to do zone by zone to determine how many air cleaning units you need and how much outside air you still need on top of the air cleaning. So we basically walk them through that process and generate the reports, and we can evaluate, LEED credit eligibility or well credit eligibility, or do energy models and develop compliance reports. So we support the engineers who are looking at applying that procedure and incorporating our technology into their design.
Okay, very cool. We could probably go all day on getting into how that's being applied and stuff. What I want to talk about though is this white paper. It's really, really excellent white paper that I had the chance of reviewing early on. And then after I reviewed it, it got hell of a lot better. You guys did a really, really great job getting into the details, really taking opinions on how people should move forward in this unsure world we're in, right? This confusing world we're in the world of IAQ. And then all the different charts and graphics and comparisons I thought were just awesome. So I want to dive into this and specifically dive into this recommendation framework, really this 4-step process that you provided. But first, I'd love to hear about kind of how the white paper came to be. And for everyone listening, we'll put the white paper link in the show notes so you can get right over to that whenever you're back at your computer. But how did this come to be, Christian?
Yeah. So we, our approach to trying to make buildings more energy efficient is to introduce this concept of cleaning indoor air rather than just relying on outside air ventilation.
Mm-hmm.
And that's something that's a bit of a paradigm shift
Oh,
for the
totally.
industry and for many of the engineers who've been using the ventilation rate procedure, from the beginning. And so we've been for some time working on sort of how do we introduce this and show the benefits of taking this approach. And it really sort of got more. We were thinking more and more about this, particularly during the pandemic, because what happened with the pandemic is that the initial guidance, or where we had made progress maybe with parts of the industry and sort of this approach, we immediately took a step back because the initial guidance was just pumping as much outside air as you can to deal with airborne viruses.
Mm-hmm.
That all makes sense. Sort of the precautionary principle prevailed, and that was what ASHRAE and others came out with. But it underscored this issue of outside air is really energy intensive. And to the extent there was pushback to the initial guidance, it either had to do with, in many cases, I don't have the fan power, I don't have the capacity to bring all this outside air, or I can do it, but gosh, my electricity bill is going through the roof. At the same time, this climate agenda is gaining more and more attention. Building decarb was becoming a bigger and bigger focus, and continues to, even certainly post the pandemic. And at the same time, we had wildfires in the West that were impacting air quality, not in the West, but here on the East Coast. So we started asking questions about, well, what if we can't bring in the outside air? What do we do? So essentially, this paper which is developing this concept we've been working on for a while called sustainable indoor air quality. That is, how do we deliver better indoor air quality that is also more energy efficient and improves buildings' resilience to outdoor air pollution? We think this is really relevant today because of the things I was just mentioning. We've got this heightened focus on indoor air quality as a result of the pandemic. At the same time, we've got this climate agenda that's, the drums are being louder and louder around building decarb, electrification, all these things, and this concerns about outdoor air quality. Outdoor air is not always fresh air anymore. That's gaining more prominence as well. But there's been a tension, right? People we've kind of gone back and forth. Let's bring in lots of outside air, but then we had the oil embargo and the issues in the 70s, and so everybody tightened up the buildings, and then we got sick building syndrome. Things got unhealthy because we had no outside air ventilation. And so it's oftentimes people view it as an either or. During the pandemic, I can improve safety by increasing outside air, but then I'm going to give up on the cost side, and safety came first, so that's what won out. But now we're focusing again, balancing a little bit, focusing on the climate side of it. But our view is that it's not an either or. We can actually do both, and there's some simple principles that can guide that, and that's really at the heart of what we do at enVerid. So the paper was really an effort to articulate this in a comprehensive way and go beyond what enVerid does and really think about this more holistically. And so we'll get into that, but that's really was the inspiration, is taking the lessons learned from the pandemic, the challenges the pandemic highlighted on how we ventilate buildings and deliver safe, healthy indoor environments, and show that show what we believe, which is they're not mutually exclusive. We can accomplish both, but we need to think holistically, and we need to think in terms of layered strategies and frameworks that we try to lay out in the paper.
Totally. And it wasn't just enVerid writing this. You had a bunch of different stakeholders from different technology providers and different service providers. Can you talk about all the other people that kind of helped you with this?
Yeah, so it sort of, the project took on a bit of a life of its own, and it made it fun. We decided in the end to collaborate with a number of other kindred spirits, if you will, other companies that are working at this nexus of indoor air quality and energy efficiency in the building space. And we sort of thought, let's collaborate and get our best ideas together. So it's not just enVerid's voice, but let's bring others into this framework, because other people are coming at it from different angles. And we also, because we believe that in the end, the solution is not just about one technology or another. There's no silver bullet in our view. It's going to take a village, if you will, to look at this issue holistically and to solve it in a comprehensive way. And so we decided to make this a collaborative project. And in the end, enVerid took the lead, but we worked very closely with the other companies. Were 75F, which looked at it from really a building control standpoint. We had Aware involved, and they're coming at it from the IAQ monitoring perspective. We had Oxygenate involved. They're a company that's developed some really efficient energy recovery ventilation systems and dedicated outside air systems. So they're looking at it from a ventilation standpoint. We had Plan LED, which is doing upper room GUV. So looking at air disinfection around, bioaerosols and the pandemic, of course. Safe Traces, we got involved, and they've developed a really innovative aerosol testing technology to help evaluate how well ventilation systems and air cleaning systems are working, particularly for bioaerosols as well. Mm-hmm. And then the last collaborator was Giga, which has developed the RESET standard. And RESET, as far as we can tell, still is the only international standard for continuously monitoring indoor air quality. And we think that's really important in terms of sort of a comprehensive solution. So we got them involved as well. So these 7 companies work together to build out and refine this framework, and is now working with us to bring this to the market and try to show how we can actually put it into practice.
Totally. Yeah, the one quote that stuck out to me reading this paper is, "So we do not have to rely on outside air for everything," and that's the piece that, like, I think that's the main theme for me. You said paradigm shift, right? And I think that's what it is. It's not the only option. And so then if there are other options, how do we then layer in all of them into a strategy? So the big thing that I wanted to walk through is this 4-step framework. I think it really lends itself well to this, longer form conversation. So let's start with the first step, which is define goals. Can you talk more about what that is?
Yeah. Well, we start with setting indoor air quality targets because we hear a lot of talk about better indoor air quality. I want better indoor air quality, and a lot of talk about solutions, different ways to try to clean the air, treat the air. And, our view is, well, we got to start with a goal in mind. When we say we want better indoor air quality, what do we actually mean? And, maybe the reason why that's not where people naturally start is because actually it's a complicated question. It's a little more complicated than I think I thought it was, particularly just being an energy efficiency guy trying to figure out all this indoor air quality stuff.
Me too. This was the section of the paper that I learned the most. I feel like this initial thing, I thought it was more simple than it actually is.
Yeah, this part and the whole discussion around CO2, which we'll probably get to, was actually the hardest part as well. But we nevertheless, we believe that we should start by defining what we mean when we say we want better indoor air quality, because then we can figure out how to get to the goal line in the way that is most energy efficiency. But if we don't know what good is, if we don't know what we mean by good indoor air quality, then trying to achieve sustainable indoor air quality, we're kind of shooting in the dark a little bit. Mm-hmm. So in our view, that's where we should start, and that certainly makes sense if we're thinking about a new building or repositioning a building or doing a tenant fit out. We do note in the paper, and I think it's right, that if we are looking at an existing building, it actually may make sense to start with our step 4, which is to just do some testing to get a baseline. And then we can say, okay, are we happy, or how much do we want to improve? And then that can guide the rest of the approach. But in principle, I think the way to start is say, okay, we want good indoor air quality, we want sustainable indoor air quality, but let's define what we mean by that. And so that's the first step, is defining the indoor air quality metrics we're going to use and the targets we're going to go for each of those metrics. And that's what the first part of the framework is all about.
Okay. And so I'll just kind of go through some of the things that I feel like I learned here, and you can kind of provide more detail to them. When you first talk about what equivalent air changes per hour means and sort of the guidance around that.
Yeah. So one of the metrics metrics that was discussed a lot during the pandemic, particularly as the guidance evolved, was this notion of of equivalent air changes per hour. I think many people who listen to your podcast are probably familiar with air changes per hour, which generally refers to a number of times in an hour that all the air in a space is replaced. Mm-hmm. And it's usually associated with ventilation air. So we're just going to, ventilate a building, and we're going to change all the air 2 times an hour, 3 times an hour. And the concept behind the notion there is that if we replace all the air, it's going to be clean, it's going to be fresh, it's going to be safe and healthy.
Yeah.
Well, if we're going to look at other approaches to, I guess the point is there are other ways to deliver clean indoor air. We can filter that air. We can disinfected if we're focused on, with upper room GUV, if we're focused on bioaerosols. The notion of equivalent air changes gets at there are different ways to achieve the goal of 3 air changes an hour, let's say. And we might be able to get one equivalent air change with the ventilation that's in the school building, for example, which probably isn't providing the 4 or 5 or 6 that are recommended with COVID. So then we supplement that with a local HEPA filter or a UV system. And so equivalent basically is the goal is, let's say, 6 air changes per hour, but let's not limit ourselves to only achieving that with ventilation air. If we can deploy HEPA filters or UV systems, then let's understand how those together on a cumulative basis get us to our target.
Okay.
So that got a lot of attention in the pandemic as people were thinking about, well, how do we account for, Joe Allen or Bill Banfield were saying we need 4 or 5, 6 air changes per hour, and a school saying, well, I can't do that. I've only got 2 or 3. And people start saying, well, what about the HEPA filter? What about the GUV? So that's where this notion of equivalent air changes came together.
Got it. Let's pause here for one more quick word from our sponsor, and then we'll get back to the show. A quick note from our sponsor, Montgomery Technologies. Their COO, Joe Gaspardoni, is easily the #1 fan of the show. No offense, of course, to any of you other hardcore listeners out there, but Joe listens to every episode, sometimes more than once, and then he gives me his feedback via email, good, bad, or otherwise. Joe is a podcast host, and I think he's maybe a much better interviewer. Joe and his team would like to remind all of you of the importance of the network layer in the smart building stack. Technology installed in buildings places a heavy burden on commercial real estate operations teams. Cybersecurity, change management, remote access, data integrity across all the different siloed systems in the building presents a significant challenge. Just knowing where everything is, how it is connected, where it is connected can be too much for thinly staffed corporate IT departments. Their primary function is to oversee the corporate network, not all of these systems in the network. So learn how a converged network fills this gap by clicking the link in the show notes. It shows how a converged network solves for all of the above and is the first step to enabling a smarter building. That makes total sense. The next question I had was the different metrics you recommend monitoring in here. So you talk about, like, maybe get into another level of detail below, like, what is acceptable indoor air quality and how do I think about defining out the metrics that matter to me?
Yeah. So the actually now for the first time, and by now I mean in February of this year, ASHRAE actually defined what is acceptable indoor air quality in terms of 14 specific, they call them design compounds now. And we have the table in our paper so people can find it there in reference to the original document from ASHRAE. This was in Addendum AA to Standard 60.1, which was published in February. So they give you a list of contaminants and they give you design limits. And basically they say if you can stay below these limits, then you're going to have acceptable indoor air quality. And then of course you can design for enhanced indoor air quality by going above those limits, and that may be in reference to the LEED or WELL or reset recommendations as well, which we summarize here. So that's sort of if you want to be specific, that's how ASHRAE defines now acceptable indoor air quality in terms of specific contaminants and design limits that they've prescribed in this addendum. Okay. We try to simplify that in the paper because 14 contaminants, some of which I can't even pronounce, and most people probably can't pronounce, is a lot to think about. And so we simplified it down to, I think it was just 5 in the end. We recommend in our paper that people define IAQ goals around particulate 2.5, PM 2.5, ozone, carbon monoxide, formaldehyde, and if they want to, maybe add CO2. But those are the core ones: PM 2.5, ozone, formaldehyde, and carbon monoxide is the one is the fourth. And we came up with this list very intentionally. And if you want, James, I can just walk through some of those. Yeah. So what we were looking at with these different contaminants is controlling for what's coming into buildings from outdoors, and sort of how hazardous it is, and also how prevalent it is. And then also what's being generated indoors, and same questions, how prevalent and how hazardous is it? And of course, trying to refer to the science and what the experts are saying here. So, not just making up as we go, but really grounding it in the science. PM 2.5, I think, is pretty straightforward. And most people who are thinking about indoor air quality, do think about this. This is the small particulate that gets in the lungs and could be an irritant, dust, pollen, these sort of things. It generally comes in from outdoors, and we generally try to control for it using various levels of filtration, particle filtration, MERV filters, and increasingly that's, people are pushing for MERV 11 or MERV 13, whereas, it's many buildings are still in MERV 8. So that was an easy one, I think, to control this sort of essentially, pollutants coming in from outdoors.
Mm-hmm.
The other one that we added to the list was ozone. Ozone is generated also outdoors, and typically is sort of pollution reacting to sunlight and heat. And ozone is a carcinogen. It's something we don't want to be breathing, and it comes in from outdoors. So it's something that we can measure, and it's a gas, unlike the particulate matter. So it's a way for us to get a view as to what's coming in outdoors in terms of gases, and specifically trying to control for this particular contaminant. The other two, as I mentioned, the other one is that we focus on indoors is formaldehyde. And this is an interesting one, and this may be where there's some new information shared in the paper that people may not be familiar with. Oftentimes we talk about indoor generated gases, we talk about TVOCs, total volatile organic compounds, or we talk about VOCs, in general. And there are hundreds of VOCs that are in the air that we breathe, but they're not all equally important from a health standpoint and in terms of their prevalence. And what the research shows, and what we have found in our own work, is if we're thinking about the indoor generated gases, formaldehyde is actually oftentimes the long pole in the tent. It's something that is actually quite common in many commercial buildings, and even at low levels is very problematic from a health standpoint. The EPA recently had some more information come out about this. And so because it's quite common, and even at low levels can be problematic, when you do calculations, mass balance calculations about these different contaminants, that's often the one that becomes sort of the long pole in the tent. And so if you can control for it, then you're going to be fine, 99 times out of 100 on all the other ones. And so we suggest that that's the one that we really focus on in these indoor environments to control those indoor gases. The challenge with formaldehyde is that it's not as easy to measure. When you think about monitoring indoor gases, oftentimes you're looking at TVOC monitors, and they're fine in terms of giving you a trend for what's happening. Is it going up and down? But if you want a granular view of what's actually going on with these VOCs, the sensing technology today, unfortunately, isn't that robust at a more granular level. So what we propose is, in terms of monitoring, is put in the TVOC sensor so you can see the trends. But if you really want to make sure you've got good indoor air quality and controlling those indoor generated gases, do twice a year at least, take air samples and look at where you are from a formaldehyde level. So that's kind of the background there. Carbon monoxide is the last one, which we say should be on that list. And it's one that can be generated indoors or outdoors. It's a result of combustion. So it can come from cooking. It can come from, the cars, driving by your building outdoors. It is also very, something that we should be worried about if it exists. And so because of that, and because it's relatively easy to monitor using continuous monitoring, we put that on the list as well. So we're really trying to get at what's coming in from outdoors that we need to worry about in terms of gases and particulate, what's generated indoors, what are the sort of the long pole in the tent, if you will, that we need to focus on to make sure we get that right, and trying to make these actionable for the most part, make sure that we can, there are tools available to monitor them.
Totally. And why CO2? So you mentioned those four, and then you said CO2 is basically optional. Why? Because I mean, that's going to be surprising to a lot of people, I would think. They think IAQ, and most people probably pretty much immediately think CO2 sensor. So why is that optional? This is probably the part of the paper where I also learned the most, and frankly spent the most time to make sure we got it right. And had the opportunity just before we published the paper, to speak to one of the authors of one of the Harvard studies around indoor air quality and productivity. And he actually complimented us on how we described the science on CO2 and that we got it right. So I felt really good about that. Cool. Essentially, the science on CO2 is that at the levels found in buildings, CO2 in and of itself is not a contaminant of concern. The science varies on this, but typically the science says you don't need to worry about CO2 as a contaminant until you get to 2,000, 3,000, maybe even 5,000 parts per million. So as a contaminant, you don't typically find those in buildings. If you did, you'd want to deal with it, but you typically don't find those in most well-operated buildings.
Nevertheless, there's been a lot of focus on CO2 and discussion about CO2. We've had Harvard studies and other studies that have talked about it. And we have LEED and WELL standards that prescribe CO2 limits. And so it's very much in the consciousness. And what is behind that is that CO2 is a good proxy of how many people are in a space and the effects on indoor air quality resulting from people and bioeffluents. It's also a pretty good, it can be used as a good indicator of how effective ventilation systems are, because if you've got people in a space and you're replacing the air, that CO2 that people are generating will be constantly, exchanged or diluted. And so you know that you have effective ventilation. But the problem with CO2 is that A, it's not a contaminant in of itself. It's only a proxy for other things, occupancy and effective ventilation. But if we're really trying to get at good indoor air quality, there are a lot of things that impact indoor air quality that don't have anything to do with people. Mm-hmm. And there are a lot of ways to control indoor air quality that don't have anything to do with ventilation. Like my favorite example is from the pandemic is you had all these people looking at wanting to use CO2 monitors to know how good their indoor air quality was and or their ventilation system is, or basically how safe they are, but they're relying on HEPA filters to clean the indoor air, which is a very valid approach. But the HEPA filter is not removing CO2. So you could have a high CO2 reading in a classroom, but be really safe from a COVID standpoint because you've got these HEPA filters blasting in the corner, and those two don't sort of work together. So those are the limitations of CO2. But there's been so much confusion about that. ASHRAE even recently put out a position document on CO2, and they basically say it's not a contaminant in of itself. It shouldn't be used as a contaminant and as the only metric of indoor air quality. It may be an effective indicator of occupancy and ventilation effectiveness if that's the approach that's being used to make sure you have good indoor air quality, but it shouldn't be used alone. And there are many other better metrics for really understanding indoor air quality, and that's what we try to highlight in the paper.
The thing that stuck out to me there was I didn't realize I think the quote in the paper was there's not a clear linkage between CO2 as a contaminant and cognitive function. So cognitive function piece has been really taking off in our industry. I mean, great studies basically showing that better ventilation equals better cognitive function scores. And people have taken that as a proxy for, okay, well, then our occupants, our employees our students or whatever the building is, are going to be more productive.
Yeah.
And it was really insightful to me to break the connection between CO2 and the scores. So can you talk a little bit more about that piece of the science?
So we don't argue the science that, let's just say, better indoor air quality leads to better cognitive function. Mm-hmm. And many of those studies have looked at CO2 as a proxy, but they've also correlated cognitive function with lower levels of VOCs or levels of particulate matter. So there's a correlation between cognitive function and some of these indicators. The question is, what's the causation? And I think when you parse that a little bit more, what you find is CO2 is used as a proxy for, are we ventilating this building well? And if we have good ventilation, then we're going to have better air quality and therefore better productivity, cognitive function. But what we try to highlight here is that CO2 is not the contaminant, it's sort of the proxy, and there should be multiple proxies used. And a lot of these studies do. They look at VOCs and they look at particulate. But the other consideration here, or the thing we try to highlight, is that ventilation is not the only way to deliver good indoor air quality and therefore good cognitive function. There are other ways to do that, and some of those other ways are more energy efficient. And if we're trying to achieve sustainable indoor air quality, we should be, incorporating these other approaches as well, not just relying on outside air ventilation.
Totally. All right, that's a great segue to step 2 in the 4-step process, which is clean indoor air. So I think we've benchmarked, or we've decided what our goals are. Why is step 2 cleaning? Why is that the start of actual action?
Yeah. So, and I think what you're highlighting here in particular is that step 2 is clean indoor air, and step 3 then is the optimized ventilation.
Yeah.
And our framework, we call it the Clean First framework, which is maybe a bit provocative, but we're trying to drive this shift in thinking that, okay, we know we want good indoor air quality. The studies say good indoor air quality leads to better cognitive function. Let's increase ventilation rates. That's how most people are thinking about this. And what we're saying is, no, if we've been thoughtful about setting IAQ targets for these different metrics we just talked about, let's then go to, okay, what's the most energy efficient way to achieve those targets? And just like in other parts of our lives, generally recycling things is a better starting point than just throwing everything out and replacing it with something new.
Yeah.
So what we're suggesting is we have a target now. Let's see how close to that target we can get by cleaning the indoor air. And then let's add the ventilation on top of that to supplement that and make sure we maintain building pressurization appropriately. So that's why clean the indoor air comes next. We have a goal. Let's see how close we can get to that goal. Let's make sure we verify and measure that. That's later in the framework. And then we'll add the ventilation piece on top rather than just go from, okay, I want better indoor air quality. Let me increase my ventilation rate. And by the way, my energy cost just went way up.
Got it. Got it. So cleaning, there's a bunch of different ways to do it, right? And this, one of the things I learned is this concept of layering the different cleaning technologies. So you have MERV 13 filters, you have sorbent filters like you guys produce, you have local HEPA filters, and then you have ultraviolet radiation. Can you talk about what you mean by layering them together and then what each of those are for? You've already talked about the sorbent piece.
Yeah. So again, this has been another fun area for us to explore and try to, simplify without compromising sort of the science behind this. When we think about indoor air quality and cleaning indoor air quality, there are actually three elements that we need to address. And we've talked about some of these. There's the particles, the dust, the pollen, these sort of things. Then there's the pathogens, which are the living organisms, the viruses and things like that. They actually move through the air attached to particles. So they're somewhat related to the particles, but we want to, there's been a lot of focus on viruses and we think that's important. And then the third piece is the gases. So when we think about layered air cleaning strategies, we're thinking about how can we address particles, pathogens, and gases by combining different technologies so that we get the air cleaning, achieve the air cleaning targets we just set most efficiently. And so for particles, what we need to keep doing is putting in these MERV filters that remove these particles. If we need really good particle filtration, we should go all the way up to HEPA filters. But at a minimum, we would recommend MERV 13 filters because they're very efficient on the particles. And by the way, they're really good on pathogens, which is how the virus moves through the air attached to a particle. So MERV 13, in our view, will become the standard. And the building code today says MERV 8 in most cases. There's now already a movement within ASHRAE to make that MERV 11, and MERV 13 will be after MERV 11. And that's how you deal with particles and base level defense against pathogens, in our view. For pathogens, we suggest targeting 6 equivalent air changes per hour, which needs some more work, frankly, in talking to the scientists. It's the best we have today, but it needs some more analysis. But if we can't get there with our MERV 13 filters, then we suggest supplementing that with local HEPA filters or upper room GUV to get you the rest of the way to the 6 or more if you want to go even above that. And particularly focus on those common areas, those classrooms, those people who are getting together in the context of a pandemic.
Got it.
So that's how we get the particles and the pathogens. We get the MERV filters, we get the particle filters, we get HEPA if we need it. We can add upper room UV if we need that on the pathogens. And then the last piece is the gases, and that's really where we've made the biggest contribution in enVerid in terms of developing these sorbent filters that capture those gases.
Got it. And when I'm looking for a target equivalent air changes per hour, how do I then add up the contributions of each of these layers to get to my target? If I'm targeting 6, how do I add up to that 6?
Yeah. So this concept of equivalent air changes, there are actually some calculators that have been developed, and we link to some of them in the paper. It's most directly relevant when we are thinking about it and a lot of these calculators are designed around particulates and pathogens. But when we think about layered strategies in the context of this framework, which goes beyond the pandemic and goes beyond just worrying about airborne viruses, what we propose is that you use the MERV filters to make sure you're addressing the PM 2.5, which is on that ASHRAE list of contaminants. It's a list of contaminants plus PM 2.5. And then we suggest you address the gases with the sorbent filter. So that's the layering. We're not replacing your particulate filter with a sorbent filter. We're layering them together so you're dealing with the particles and the gases. And then the pathogens is really, during a pandemic, you need to make sure you have high MERV filters, or you need to supplement with HEPA or upper room GUV. So that's how we would layer. But if you're thinking about the pandemic, thinking about your equivalent air changes in that 6 goal, which is really for a pandemic mode, That's where these calculators have been developed. ASHRAE's got some, there are others, they're linked in our paper, and use those to do those calculations.
Got it. Okay. Okay, step 3. This is where we bring in ventilation. And you guys don't say bring in ventilation, you say optimize ventilation. So can you talk, we already talked a little bit about ASHRAE's 2 different procedures and how you guys are going into the IAQP option of the 2. Can you talk about what you mean by optimize?
Yeah. So as I said before, the ventilation rate procedure, which is what most people are using today, is a prescriptive procedure. It just says, I have this many people, I have this much area, this is how much outside air I'm going to bring in, and I'm ignoring the MERV filters or the sorbent filters or whatever else I have going on. So the optimization is, let's account for what we've accomplished with those other air cleaning systems towards our IAQ targets we set in step 1, when determining that ventilation rate that we now need on top of air clean to make sure we get the, achieve that sustainable indoor air quality, that efficient, air quality. And so the optimization is really pointing us towards the IAQ procedure, which is a performance-based approach to determine that minimum or excess, if you want to go above minimum, you can, of course, ventilation rate. And so that's really what the optimization means. And we suggest further, as we say in the paper, is to optimize that ventilation rate around the indoor air quality procedure, accounting for the air, which allows you to account for the air cleaning capabilities or solutions that you've deployed. But the further optimization then is also to make that ventilation that you still will need most efficient by incorporating energy recovery. And so that's part of the optimization that's within step 3.
Got it. Okay. That piece, when I read it, I was like, okay, I'm familiar with that. Like I got like 20 pages in and I'm like, okay, this first part that I didn't feel like was new to me. Was there anything new to you when you were doing that step?
Yeah, I think one of the things that has really started to resonate when we think about optimizing ventilation is how that can not just improve the efficiency of your ventilation system because you're accounting for the air cleaning capabilities here, but it actually helps with this whole electrification agenda. And there's been a lot of focus on heat pumps, and in the paper, we're able to connect the dots to tie it into the heat pump craze as well. And the whole notion there is that when we use the IAQ procedure with air cleaning, because we're able to reduce the heating and cooling load on the building, we can actually make deploying heat pumps more cost effective because you don't need as many heat pumps. And by the way, if we're trying to retrofit a building with heat pumps, we're going to reduce the electrical service. So the cost to upgrade electrical service in some of these buildings we're trying to electrify can be significant. And if we can go from 30 heat pumps to only needing 20 heat pumps because we're conditioning less cold outdoor air in the wintertime, not only do we extend the range of these heat pumps because we're going to have more cleaned recirculated air, so we're not going to limit the capabilities of the heat pump as much, but it's also going to be more cost effective and not impact the electrical load as much, which will support this. So the beauty of this clean first approach, like I said, it's really designed to be a comprehensive holistic approach. And what we start to see is that the air cleaning solutions integrated with the IAQ procedure with ventilation with energy recovery also enables going further with heat pumps or other solutions that help with the decarbonization agenda.
Yeah, and less capital costs for this transition that is definitely necessary from a societal
and
standpoint.
Maybe, James, I can give a quick plug. There's NYSERDA's done some really good work around something they call resource efficient electrification. It's come out of the Empire Building Challenge work that they've done, and some folks from RMI and others have been involved in this. And their whole framework starts with, let's reduce the load as much as we can, because it makes it easier to transition to electrification. And that's exactly what the Clean First framework allows you to do, is let's first reduce the load by cleaning the indoor air as much as we can, optimizing that ventilation with energy recovery, and then it makes it easier to do the heat pumps and the other things we want to do to electrify buildings. So a plug for the work that the team working in the Empire Building Challenge has done in this resource efficient electrification framework, I think is worth people having a look at.
Yeah, definitely. Okay, step 4, monitor. I wrote down monitor, validate, control. I don't remember if that's exactly what you guys called it, but I think I have a lot of questions here, so I wanted to get to this for sure. But can you talk about, just kind of introduce this step?
Yeah, so we actually, our order is validate, monitor, and control. And the reason for that is that we want to make sure that these air cleaning systems that we've deployed are doing their job once the building comes online. And so the first step, and actually the updated ASHRAE standard around the indoor air quality procedure requires you to go in and do testing post occupancy and make sure that with your optimized ventilation and your air cleaning systems, you're delivering against the design targets that are listed in the standard. So the first validation is, let's get in there, let's do air sampling around, formaldehyde and these other contaminants that you can't do with monitoring. Make sure everything is working right off the bat. And then we add the monitoring piece next, because we want to then continuously monitor that. And it's almost like fault detection, right, for indoor air quality. We want to make sure the air cleaning system, the ventilation system, everything's working. Fault detection can actually help us do this. And some fault detection platforms, I believe, are sort of looking at IAQ as well. But it's let's validate the design in practice post occupancy, and then let's monitor it to watch that heartbeat and make sure we maintain those IAQ targets from step one. And then the last piece is, ideally, let's just not monitor it in a separate platform, but let's actually integrate the IAQ monitoring with the building management system so that we can make adjustments dynamically and hopefully automatically to account for changes in occupancy, changes in outdoor air conditions during wildfire season or on a hot ozone alert day. This doesn't have to be a static design, right? Mm-hmm. We can make this dynamic by tying the monitoring into the control system and allowing us to dial up or down air cleaning systems, or dial up or down that outside air ventilation to most efficiently and continuously achieve those IAQ targets.
Yeah, that's the piece that I wanted to ask you a little bit more detail around. So to my knowledge, so if you think about this world that has happened over the last 5 years or so, where we've had this explosion of these, dedicated, standalone, vertical, full stack IoT, basically IoT stacks, right? So designed for indoor air quality, CO2. I have one right here, over my shoulder here in my room. Typically, most of the time, those are not being pulled in and used for some sort of closed loop control sequence. And if they are, typically it's just CO2, right? And there's typically an HVAC silo and there's an IAQ silo, and most of the time those are not branched. So
like back in your foundations class, James, talking about these different silos and different jobs that these different systems don't do them together.
Yeah, exactly. So that's the paradigm that this industry has come to.
Yeah.
When I read that in your paper, I was like, okay, cool.
Yeah.
But is that happening, right? Yeah. How is that happening? I'd love to hear from the people you engaged with in writing this.
Yeah.
Is that the next step with writing control sequences?
Yeah, I would say that it is step 4 in our framework, and it's probably the step that is least mature in terms of market readiness, for all the reasons that you were just referring to. We did collaborate with 75F on this piece, because what they have done is tried to develop a, cloud first IoT based, BMS system that can do a lot of these things natively, and they are doing some of them today. They are able, their system does a lot of, does things like, can be adapted to occupancy, which many BMS systems can do today, using demand control ventilation based, sequences.
Yeah.
But they can also isolate parts of the building, and they have a broader IAQ monitoring capability that is natively integrated into their building management system. So we think they're a great example of
someone on the forefront of this.
Yeah, forefront of how we actually make what we talk about in this paper a reality. But I think that it's probably the exception more than the rule yet in terms of actually being deployed in this way.
Yeah.
Hopefully we lay out a roadmap for how it can be done and the value of doing it in this way. I think the capabilities are coming with companies like 75F, and hopefully we'll see more of that in the field going forward.
Yeah, because it just follows from logic that if indoor air quality is not just about ventilation anymore, well, then we need ventilation control sequences that take everything else into account at some point.
Well, and there are more and more. I mean, there are other companies out there. It's not just 75F, but that are deploying sensors outside the building, so they're adapting to outdoor air quality. They've got sensors or occupancy readers in the space, and they're looking at the weather, and then they're doing optimization, using machine learning algorithms to basically figure out what's the right sequence for the next 15 minutes, accounting for how many people am I building, what's going on outdoors, what's the weather going to be in the next hour. And so there are startups that are doing this, and I think what will happen over time is that will become more the norm than the cutting edge, and that's what we're sort of pointing to in this fourth part of our framework.
Yeah, and I think that's another area. This is another area, in energy versus IAQ, and then all the different ways to ensure IAQ. Right, that's a optimization problem that's too complex for most control systems today. And so that's where you need the startups to come in and say, okay, there's a better way to actually do this, improving upon, PID loops, essentially. So you guys close this case study out with, you close the white paper out with the case study, and it just basically tied it home for me, which is you went into this building at the University of Miami and decreased the ventilation, and yet, which saved a lot of energy, and yet air quality improved. Can you talk a little bit about that?
Yeah, so we did a project a couple of years ago at the University of Miami in their wellness center, where they were not satisfied with the indoor air quality they were getting. They had tried to just pump in more outside air, but in Miami, that was really intensive, energy intensive, and their systems had some limitations. And so they were looking for other ways, and they basically were introduced. We didn't call it sustainable IAQ or clean first at the time, but that's essentially what we did. And so in that case, we deployed. They had MER filters for particulate, and we weren't worried about it yet, but bioaerosols. But they didn't have anything on the gases side, and so they were just relying on outside air ventilation to control those gases. And so we added the sorbent filters as part of these HLR modules that we deployed there. And as you said, we were able to reduce the outside air by 75% relative to the VRP baseline that they were using before. And that reduced the HVAC peak demand by 41% and reduced their HVAC energy consumption by 36%. It unlocked $20,000 a year in savings, about 33 cents per square foot, normalized for their area there, and improved indoor air quality. We lowered VOC levels, we lowered particulate levels, we lowered even the CO2 level because we had our CO2 scrubbing unit installed there. And so we put it in here because we're like, this is an example, of where this works. Now, they didn't have the dynamic controls piece, right? So that last piece wasn't there. We did go in and validate. We did testing. In fact, NREL came in and did both energy and IAQ M&V to independently verify the improved IAQ, even with 75% less outside air. But we didn't have the sort of continuous monitoring or that control piece, which again is sort of where we think the cutting edge is. But the rest of this can be done today. It's been done before. That project is a great example of it.
Yeah, totally. Let's close out with ROI. So if I think about this from an owner standpoint, a lot of owners have outside air dampers, right? They have the ability to throw the outside air dampers open like they did. A lot of them did at the beginning of COVID, but not a lot of owners have your guys' technology. Not a lot of owners have all the other technologies that we talked about here, including monitoring, including controls that are capable of what we talked about. So how do I think about buying all these new things, and given that investment, what's the return? How do I think about the return on investment with all of these investments?
Yeah. So if we think about it in terms of the steps, step one is coming up with the targets, defining the metric, coming up with the targets. Many people can probably do that themselves based on what we offer as recommendations in the paper. Maybe you want to get a little consulting help on that, but that shouldn't be too expensive if you want some help with that. And many vendors will provide that as part of their sales process. We can help with that. Aware, trying to sell you IAQ monitors, they'd be happy to talk to you about the metrics and targets that we have in here and their view on that as well. So that's pretty straightforward. The second piece around air cleaning. Air cleaning, when it unlocks energy efficiency benefits, can pay for itself. We do lots of projects where by deploying our system, which of course does cost some money, and then optimizing that ventilation rate using the IAQ procedure and reducing the tonnage of cooling capacity required because we're not bringing as much outside air, we're often doing projects with a negative first cost or a payback that's certainly, well inside 3 years. And so it may not be intuitive initially, putting in more air cleans is going to cost more money, but it can be very cost effective when we couple this, when we do it the way we outline here in terms of connecting it to the ventilation rate. The University of Miami project we were just talking about, simple payback on that's about 3 years. So pretty reasonable, especially for a public institution that probably, could even go a little bit longer if they needed to. The ventilation piece, everybody's got to ventilate their building. We're just going to make it more cost effective by conditioning less outside air. So I would not necessarily view that as a big cost add. Maybe you want to go spend a little more money on a more efficient energy recovery system from AuctionAid or something like that. But those systems I think are pretty cost effective, and they're going to pay for themselves in their efficiency, particularly when they're coupled with the air cleaning the way we recommend. The IAQ testing. So we do a lot of IAQ testing. When you can actually get lead points, extra lead points by doing the IAQ procedure as outlined in this paper, but you need to do some testing to validate the performance. And so usually that's done for a couple $100. We take air samples, we send them to a lab. Maybe there's some travel on top of that, so it can get a little more expensive than that, but it's not crazy expensive. IAQ monitoring, I don't have good rules of thumb around what Aware or others sell their sensors for. So I'm not going to comment on that. And certainly, from a control standpoint, everybody needs a control system. The question is, do you have a smart one? And where are you in a cycle of upgrading your control system? So I guess the long and short of it is that this doesn't have to cost a lot of money. In fact, it can save you money. I mean, that's the whole concept with sustainable indoor air quality is let's do better indoor air quality more efficiently, which efficiently means cost effectively as well.
Totally.
But there's also the marketing benefits. There's also you're avoiding penalties under local law 97 in New York that are coming on carbon emissions. So there are many ways to pay for this. If it's not going to be cost effective, utility incentives will pay for a lot of the solutions that we're describing in this paper as well. So, it's going to vary depending on the building. Implementation costs are very building specific, of course. It's going to vary based on the climate zone and the cost of electricity. Reducing outside air ventilation rates in San Diego doesn't matter because as long as the air quality is good, you're getting outside air at temperature for basically free. So, where we find the strongest value proposition for what we do and for this framework as a whole is going to be in markets with hot, humid summers, cold winters, medium to high electricity rates, and then you throw on utility incentives and carbon taxes, and you're in great shape. So that's how we think about the economics. Payback should be, very reasonable if you put it all together and do it the right way.
Awesome. Well, thank you for writing this paper and working so hard on it. I know you worked very, very hard on it. So thank you for doing that. Thank you for explaining most of it in a little over an hour. So that's awesome. Let's close out with some carve-outs. I'd love to hear any links you recommend that we share with people, books, podcasts, movies, things that have inspired you on your journey.
Well, my first recommendation is the Nexus podcast by James Dutch. You should check it out, especially this episode. You can also find our white paper at whitepaper.enverid.com/sustainable IAQ. So I'm going to plug that.
Nice.
But getting out of the work mode for a moment, I know on these podcasts you often ask people about a good book or podcast or something, and I don't read as much as I'd like. But the last page turner that I got into and really enjoyed was a book called Unbroken by Laura Hillebrand. Have you read that?
Nope.
So Unbroken is about a World War II Army Air Force. The Air Force was probably Army at the time. Pilot, or I think it was a pilot, Louis Zamperini, who was shot down by the Japanese over the Pacific during the war. And it's this amazing story about survival and faith. And he was he was at sea for a long time in a life raft, fighting off sharks and trying to sustain himself with what he could catch and a little bit of rain he got, and then he was in the POW camps for a long time. But he was resilient, and it's an amazing story. And so I recommend it. I think there's a movie out now, so if people want the Cliff Notes version or the action, on the screen, check that out. It's a good read and probably a good movie, although I haven't seen it yet. Love it.
Sounds like it might have had an impact on you to stay resilient and keep going as a startup CEO.
Yeah. Well, it does put things in perspective, right? We get stressed out about little things at work every day, but this guy went through and survived, and how he came out at the other end is truly, it was inspiring. So it puts life in perspective and makes you appreciate the little things a little more sometimes.
Awesome. That reminds me of Man's Search for Meaning by Viktor Frankl.
Yeah.
Which was an all-time great for me. If anyone hasn't read that, they should definitely
good.
check it out. Well, those are two very amazing book recommendations. We'll leave it at that. Thanks, Christian, for coming on the show. This was super fun.
Thanks for having me. I appreciate it.
All right, friends, thanks for listening to this episode of the Nexus Podcast. For more episodes like this and to get the weekly Nexus newsletter, which, by the way, readers have said is the best way to stay up to date on the future of the smart buildings industry, please subscribe at nexuslabs.online. You can find the show notes for this conversation there as well. Have a great day.